Hello, my dear students. Welcome to my YouTube channel, that's Concepts of Chemistry. Before starting today's lecture, please do subscribe my channel. My dear students, today's topic for the lecture is the valence bond theory, that's hybridization of the atomic orbitals. In the previous lecture, we have done about the covalent compound, the methane is CH4. And I have given you two types of observation, the theoretical observation according to the concept and the experimental observations that we got in reality, but they were not matching with each other. To explain the experimental observations, so we are going to study the subject or topic called hybridization of the atomic orbitals. So let me write the experimental observations for the methane, and they are, we are talking about methane CH4. The experimental observations were all the bonds were of equal strength. In CH4 molecule, and second experimental observation was that all the bond angles were equal the structure is three-dimensional. The structure of CH4 is three-dimensional with a bond angle of 109 degrees and 28 minutes. So now let's talk about the CH4 in detail. I'm going to take the example of CH4, the hybridization, and we are going to discuss these experimental observations on the basis of hybridization. So let's start. I'm writing the molecule is CH4. Here the central atom, in case of CH4 is carbon. Now let me write what is central atom. The atom to which maximum bonds are formed. In case of CH4, carbon is forming 4 bond and hydrogen is forming 1 bond. So carbon is forming the maximum number of bonds. So carbon is central atom in case of CH4. So that means we are going to talk about the carbon now. What's the atomic number of carbon? It's 6. What's the valence shell electronic configuration of carbon? It's 2s2, 2p2. Now let's make this electronic configuration in the box forms of orbitals. Now the 2s subshell has only one orbital, so I'm drawing only one box. It's 2s. The 2p subshell has three orbitals, that's 2px, 2py, and the 2pz, and they are degenerate. So we are making three boxes together. What are degenerate orbitals? The orbitals having equal energy are called degenerate orbitals. So 2px, 2py, and 2pz are degenerate orbitals. Now, how many electrons does 2s subshell is having? It's 2, so that means the 2 electrons will come in 2s orbital, one with the spin of plus 1 by 2, another with the spin of minus 1 by 2. Now 2p is having 2 electrons, so we will fill the two electrons in degenerate orbitals according to the Hund's rule. Hund's rule states that firstly all the orbitals will get one electron each. After that the pairing will start. So but we are having only two electrons. The first electron will go into px and the second one will go into py. Now what is covalent bond formation? When the two atomic orbitals containing one electron each but with opposite spin overlaps with each other will form the covalent bond. So here we are having total of 4 orbitals in which the one orbital, that's 2s, is having 2 electrons. So 2s orbital will not overlap with each other because it's full of electrons. Now 2px is having 1 electron, so it needs one more electron in that orbital. 2py is also having 1 electron, so it needs one more electron in that 2py orbital to make the covalent bond. And 2pz is vacant, so it's not going to form any bond. So that means here the carbon will form only 2 bonds, but according to the Lewis structure the carbon forms 4 bond in CH4. So what we are going to do? Firstly, this is called ground state. This is called ground state. Now, to make 4 bonds, we need 1 electron each in all the 4 orbitals. Only then carbon will make the 4 bonds. So, for that thing, what we are going to do? We are going to do actually jump this electron from 2s to 2pz. The electron from 2s orbital is promoted to 2pz orbital. So, that will be called as excited state. Let me draw that thing again. That's the box form of atomic orbitals. Here it's 2s, that's 2px, that's 2py, and that's 2pz. And now we are having 1 electron each in all the 4 atomic orbitals. And this is called as excited state. And this is called as excited state. Now what next will happen? What next will happen is that these 4 orbitals, one of 2s, the 2px, 2py and 2pz, will intermix with each other. Firstly, they will, all the 4 orbitals, I am writing, all the 4 orbitals. Which orbitals? One orbital of 2s plus 3 orbitals of 2p will intermix with each other. They will intermix with each other to form firstly homogeneous mixture. To make you understand, I am using this word, the homogeneous mixture. After that, in this homogeneous mixture, what we are having? In this homogeneous mixture, there is a mixing of 1 orbital of 2s and 3 orbitals of 2p. That means in this homogeneous mixture, we are having 1 s orbital and 3 p orbital. That means in this homogeneous mixture, we are having 25% of s and 75% of p character. Now, how many orbitals have mixed in this mixture? 4. Now divide this homogeneous mixture into 4 parts. I am dividing this homogeneous mixture into 4 parts, or we can say we are dividing this homogeneous mixture in which 25% of S is there, 75% of P is there, into 4 parts, or we can say the 4 orbitals. Now what next I'm writing? Now this homogeneous mixture will split into 4 new types of orbitals. Orbitals called hybrid orbitals. In which each orbital will have 25% of S character and 75% of P character. So we can write it like sp3. So we are going to have 4 new type of atomic orbitals called hybrid orbitals, and here the name of that hybrid orbital will be sp3. This sp3 signifies that S is 25% and P character is 75% in all the 4 new atomic orbitals. So here the 4 orbitals have mixed, 1 orbital of S and 3 orbitals of P, and they will form the equal number of new hybrid orbitals. Assume if 5 orbitals were mixing, then we will get the 5 orbitals, hybrid orbitals. If assume 3 atomic orbitals are mixing, then we are going to have 3 new hybrid orbitals. So here 4 atomic orbitals are mixing, so here we are getting 4 new types of hybrid orbital, and the name of that hybrid orbitals will be sp3. So I am making 4 hybrid orbitals, and again they are all degenerate, so we are making together the 4 atomic orbitals. So these are the 4 atomic orbitals, and name of each atomic orbital will be sp3, sp3, sp3 and the sp3. That means each orbital is having 25% S character and 75% P character. So that's why the name is sp3. 1s and 3p, 1 part S and 3 part P. That means 25% S character and 75% P character per atomic orbital. So here we got 4 sp3 atomic orbitals. Now how many electrons we were having? We were having total of 4 electrons. So in these atomic orbitals there will be redistribution of 4 electrons according to Hund's rule. Hund's rule states that firstly all the atomic orbitals will get 1 electron each. After that pairing will start. So we are having 4 electrons, the first electron in first sp3, second electron in second sp3, the third electron in third sp3, and fourth electron in fourth sp3. Sorry. Now carbon has to make covalent bond with 4 hydrogens. We are having 4 hydrogen atoms. What's the atomic number of hydrogen? It's 1. Configuration is 1s1. So I'm writing hydrogen. The hydrogen configuration is 1s1. So the s orbital of hydrogen will now overlap with sp3 orbital of carbon. So here we got a sigma bond, and that sigma bond will be in between the s orbital of hydrogen and sp3 atomic orbital of carbon. So here the type of sigma bond will be sigma s sp3, because s orbital of hydrogen has overlapped with sp3 hybrid orbital of carbon. Both of the orbitals the s of hydrogen and sp3 of carbon is having 1 electron each, so now they will easily overlap to form the covalent bond. Now same thing goes to the second hydrogen. That's a hydrogen, configuration is 1s1. The s atomic orbital containing 1 electron of hydrogen will overlap with the sp3 hybrid orbital of carbon containing 1 electron. Now let's talk about the third hydrogen. Now it's the third hydrogen. The configuration is 1s1. Here again the s orbital of hydrogen containing 1 electron will overlap with the sp3 hybrid orbital of carbon containing 1 electron. So there's the formation of covalent bond. Now again these bonds are of type of sigma s and the sp3. The bond formed between the s orbital of hydrogen and sp3 hybrid orbital of carbon. The same with third bond is also sigma s sp3. And let's talk about the fourth hydrogen. It's again 1s1. So again the s orbital of hydrogen containing 1 electron will overlap with the sp3 orbital of carbon containing 1 electron. So here's the again formation of covalent bond will take place, and that sigma bond will be sp3. Now here you can easily imagine that, or we can see easily observe that, all the four bonds are sigma s sp3. So all the four bonds will have equal strength and equal bond dissociation energy. So that means all the bonds in case of covalent compounds containing minimum of 3 atoms will be of equal strength. So now let's make the orbital diagram now. What we were having? Carbon. Here the hybridization of one orbital of 2s and 3 orbitals of 2p has taken place. Now what's the structure of s orbital? What's the shape of s orbital? It's spherical. It's spherical. Now we are having 3 2p orbitals. That's x, that's y, and that's z. Now here first of all this is 2px. Hopefully you got it in 3D. This is 2py and this one is 2p z. Now what will happen? These 4 orbitals will intermix with each other. So what we are going to have? We are going to have 4 new atomic orbitals after mixing. I'm writing formation of 4 new atomic orbitals will take place, that I have already discussed. Because 4 orbitals are mixing, so 4 new hybrid orbitals will form. So how's its structure will be then? First of all, that atomic orbitals will be named as sp3. We are getting 4 sp3 atomic orbitals. So their shape will be like, first of all, the one lobe of p will grow in size and another one will remain small. That's my first sp3. Now that's our big lobe and small lobe. That's again sp3. That's again sp3. and that's again sp3, and in the center we are having the nucleus of carbon. So these are the four atomic orbitals that have been formed by mixing of one s orbital that's spherical in shape and three p atomic orbitals that double in shape, and we are going to have four sp3 atomic orbitals, in which if I talk about the single sp3 hybrid orbital, then you are having one bigger lobe and one smaller lobe. That's sp3, and we are getting it in 4 in number. So that's why I have made it like this. I have made it like this. Now let's make a bond line formula. I'm writing carbon over here. So what next? Let's make it over here only. That's again sp3. Now what's gonna happen? The 1s of hydrogen is going to overlap with the sp3 orbitals of the carbon. We are having now hydrogen and its 1s orbital, and we are having these are 4 in number. So that means, just imagine it, the 1s of hydrogen overlapped with sp3 of carbon. Here also the 1s of hydrogen overlapped with sp3 of carbon. Here also the 1s of hydrogen overlapped with sp3 of carbon, and here also the 1s of hydrogen overlapped with sp3 of carbon. So that's exactly the structure of CH4, the orbital diagram of CH4. So how can I write it? Let me show you. Now here's the carbon, here's the hydrogen, and this is the hydrogen. I'm trying to draw this diagram in 3 dimensions. So these two bonds are actually on screen. Now after that, this is called wedge. Wedge means this hydrogen is coming out of screen. Just imagine it in 3 dimensions, that this wedge bond is coming out of the screen. This is called wedge, and this is called dash. Hydrogen, this is called dash. Dash is going in the screen. The dash bond is going in the screen, wedge bond is coming out of the screen, and the other two are on the screen. So this is the 3-dimensional diagram of CH4, and here all the bond angles are equal. That is, the value is 109 degrees and 28 minutes. This is also 109 degrees and 28 minutes. This is also 109 degrees and 28 minutes. This is also 109 degrees and 28 minutes. After that, here this is also 109 degrees and 28 minutes. This is also 109 degrees and 28 minutes. So all the bonds are equal with a value of 109 degrees and 28 minutes. And now let me make this diagram again to explain the second observation. So I'm writing, this is the carbon, this is the hydrogen, this is the hydrogen, this is the wedge, this is the wedge hydrogen, and this is the dash hydrogen. Now from hybridization what we have proved that all the bonds are of equal strength. That means all are the sigma bond with that have been formed between, it's a sigma bond of type sp3. This is also a sigma bond of type ssp3. This is also a bond that sigma ssp3, and this is also sigma ssp3. So all the four bonds are of equal type. All the four bonds are of all the four bonds are of same type. That's why they are all of equal strength. So I'm repeating it again. All the bonds are sigma ssp3. All are of same type. That's why all are of equal strength. So that's hybridization. I'm repeating it again. Here in this case, 1 s orbital and 3 p orbital. Total of 4 orbitals have intermixed with each other to form the set of 4 new orbitals containing 25% s character and 75% p character. That's why we named them sp3. sp3 means 1s, or we can say the 1 part s and 3 part p. That means 25% s character and 75% p character per atomic orbital. That means 4 sp3 atomic orbitals have been formed in the carbon, to whom the 1s of hydrogens have overlapped to form the sigma bond of type sigma ssp3. Now all the 4 bonds are of same type, that's sigma ssp3. That's why they are of equal strength. So that's hybridization. Now let me write some points about the hybridization, and these are very important. I'm writing some important characteristics of hybridization. The very first point: hybridization is the process of mixing of pure atomic orbitals to form equal number of equivalent orbitals known as hybrid orbitals. In this example, we have mixed 4 atomic orbitals, that's 1 of s and 3 of p. That's why we got total of 4 new hybrid orbitals. So I'm writing hybridization is the process hybridization is the process of mixing of pure atomic orbitals to form equal number of new orbitals, equal number of new orbitals called hybrid orbitals, called hybrid orbitals. Now let's talk about the second point. Hybridization will take place at the time of bond formation only. That means non-bonded atoms are not hybridized, but bonded atoms can be hybridized. Let me write this thing. Hybridization takes place only at the time of bond formation. Only at the time of bond formation. That means here, if if carbon is coming, sorry, if hydrogen is coming to form the bonds with the carbon, only then hybridization will take place in carbon. The sp3 hybrid orbitals will form. If we take away the hydrogen from the carbon, the sp3 will convert back to the 2s and the 3 2p orbitals. So hybridization is a process that takes place only at the time of the formation of the bond. Non-bonded atoms are never hybridized. I'm repeating it again. The hybridization will take place only at the time of bond formation. The non-bonded atoms are not hybridized. If we take away the hydrogen, then carbon, the sp3 orbitals of carbon will convert back to the 2s and the 3 2p orbitals of carbon. Now, the third point. Diatomic molecules. Diatomic molecules are never hybridized. What are the diatomic molecules? Let me give you the example like O2, N2, Br2, Cl2, I2, etc. So, for these diatomic molecules, we are having molecular orbital theory, which is the last topic of this chapter. I'm going to make the video on that also. So, diatomic molecules are never hybridized. Now, the fourth point. The fourth point is hydrogen, the only element. The hydrogen is hold on. Hydrogen, in case of hydrogen, will never undergo hybridization process. The hydrogen will never undergo hybridization process. Why so? Because in case of hydrogen, we are having only one subshell with only one orbital, that's only 1s1. The only first shell with only one subshell, the s orbital with only one electron. So there is not availability of p orbitals. So that's why hydrogen will never undergo hybridization process. I'm repeating it again. Hydrogen is never hybridized because hydrogen is having only one orbital and that's of only s. Hydrogen is not having p orbitals. So hybridization will not occur in case of hydrogen. Now let's talk about the fifth point. The hybrid orbitals have fixed orientations in space, so it has a fixed geometry. The hybrid orbitals have fixed orientations in space, has fixed orientations in space, or we can say 3D region around nucleus. So every hybridization has fixed shape. So every hybridization has fixed shape. Now let's come over here. So this is the thing. Sorry. Now every hybrid orbitals have fixed orientations in space. Here you can see that here the fixed orientation stands for fixed angles. So here we are having 109 degrees and 28 minutes, the fixed angles in 3D space. Here what I have told you in this diagram, that the bonds are on the screen, the wedge is coming out of the screen and dash is going inside the screen. So it's in 3 dimensions. So they are having equal angles, and they are having the fixed orientations in the space, and they also have a fixed name. Here this shape is called tetrahedral shape. Here this shape is called tetrahedral shape. In the very next lecture, I am going to talk about different types of hybridizations and their structure along with their angles, along with their names in the next lecture. Here we are just talking about the introduction to hybridization. So in case of sp3 hybridization, the shape is tetrahedral, having a bond angle of 109 degrees and 28 minutes in 3 dimensions. And this angle will vary according to the lone pairs, which we will discuss in the next lecture. So I'm repeating it again. The values of angle will vary according to the bond pairs, the lone pairs, and the electronegativity of central atom or the another atom, which we will discuss in the VSEPR theory. The valence shell electron pair repulsion theory deals with this thing. Here we are just studying about the introduction to hybridization. Now the sixth point. Now let's talk about the sixth point. Here in this point, we have jumped the electron from 2s to the 2p. In this process, the energy is required. The energy required to jump the electron is called the promotional energy. Here this is the promotion. This is the promotion of electron from 2s to 2p. Now here the energy is required, and that energy is called promotional. The word is promotional energy. So here the energy required is called promotional energy, in which the energy which is required for the process, that is jumping the electrons from 2s to the 2p to make the 4 unpaired electrons. I am repeating it again. The electrons are promoted from 2s orbital to the 2p z orbital, and for this process the energy is required, and it is called promotional energy. But when the hydrogen makes the sigma bonds with the sp3 orbitals of the carbon, the whole process is concerned with the release of energy. I am writing, when the bonds are formed, between 1s of hydrogen and sp3 of carbon, the energy is released. The energy is released, which also compensates the promotional energy. And this is a very important point. The energy released during the formation of bond between the 1s of hydrogen and the sp3 of carbon, obviously it's an exothermic process, and the energy is released, and the promotional energy also gets compensated. If promotional energy is not getting compensated, that means the formation of that molecule is also not possible. So I'm writing over here in the important points the sixth one. During the formation of new bonds, the energy is released the energy is released which compensates promotional energy, which compensates promotional energy, comma, only then the formation of that covalent compound, only then the formation of that covalent compound is possible. Full stop. I'm writing again. If promotional energy is not compensated, if promotional energy is not compensated, then formation of that compound is also not possible. That covalent compound is also not possible. Now let's talk about the very last point. Here, the mixing of atomic orbitals also consumes energy. I'm writing it again. Over here, the mixing of atomic orbitals, the mixing of atomic orbitals also consumes energy, which has to be compensated when new bonds are formed. So the mixing of 1s and the 3p orbitals also consumes energy. For that, when the new bonds are formed between the 1s of hydrogen and the sp3 of carbon, that energy required for hybridization or the mixing of atomic orbital has to be recovered or compensated. Only then hybridization process is possible. So this is the last point I'm writing. The seventh one, the energy required for the hybridization, that is mixing of atomic orbitals, is also recovered during the formation of new bonds. During the formation of new bonds between hydrogen and carbon. So the energy required for hybridization is also recovered or compensated when the new bonds are formed between the hydrogen and the carbon. So that's all about hybridization. I hope you all understood today's lecture, and it's a very, very important topic. And this topic has also explained the experimental result. In case of CH4, all the bonds were of equal strength because the overlapping was of same type, that is between the 1s of hydrogen and the sp3 of carbon. So all the four bonds are of same type, that's sigma s sp3. That's sigma s sp3. That's why they are all of equal strength. So I have written some important characters of hybridization also. In the very next lecture, we are going to discuss different types of hybridization along with their structure, along with the angle, along with the lone pairs. After that, in the very next lectures, in the incoming lectures, we are going to discuss about the change in the angles according to the lone pairs and the electronegativities of the element, and that topic will come under the theory called Vesper theory, that's valence electron pair repulsion theory. I think that's all for today. I hope you all understood today's lecture. If any student who wants to book a paid one-to-one online class to clear their doubts, then she can contact me. My phone number is mentioned on thumbnail of this lecture. Please do like, subscribe and share this channel to maximum number of students. Don't forget to press the subscribe button. Stay blessed.